equilibrium, but rather something, I think, unexpected, at least to me, about equilibrium physics. And Luca, who's not here, sort of allowed me to do this. Okay, so this is a recent collaboration with Zohar Komorgatsi. I guess the laser won't work, but that's fine. With Zohar and Fedor at the Simon Center for Geometry and Physics, as well as my postdoc Yi Chu and my student Xiaoyan. Okay. So the motivation for this talk is that we have this conventional wisdom in sort of textbook thermodynamics and statistical mechanics, which is that if we sort of heat a system up to very high temperature, it will be in a disordered phase. Okay. And there's a very simple argument for this from 19th century physics. So finite temperature, we want to minimize the free energy F, which is equal to the energy E minus temperature T times entropy S. And at high temperature, it makes sense that we would want to sort of maximize the S in this formula, i.e. entropy. And if we think about sort of building a phase with very high entropy, then we sort of expect this phase to be very disordered. So this is a sort of cartoon that shows you that if there's one thing that even sort of pop sci readers understand about stat mech, it's that sort of entropy is a measure of disorder, randomness. So, okay, that's a sort of typical argument that high temperature systems are disordered. We can sort of follow this line of thermodynamic reasoning a little bit farther. So at a phase transition, if we start heating a system up, and at some critical temperature Tc, we transition from one phase in blue to another phase in red. Remember that we're always minimizing the free energy. So if there are two different free energies associated with these two competing phases, we always pick the smaller of the two. And from the laws of thermodynamics, the entropy S is minus dF dt. So this means that we're guaranteed that the higher temperature phase, in red in this picture, has this higher entropy. Okay. So that will always be true. And therefore, if we sort of look at this kind of qualitative phase diagram, we have temperature on the y-axis and some tuning parameter h. This might be, well, could be anything other than temperature. On the x-axis, maybe this is some kind of external field or other tuning parameter in our theory. We sort of expect that A, the phase which kind of proliferates at high temperature, is the disordered phase, and B is the ordered phase, okay, if we have a sort of typical phase transition. And in particular, this means that if we're studying, for example, a kind of conformal field theory, as we tune this parameter h, which would correspond to a relevant operator in the field theory, we would sort of expect that at the critical point, when we heat it to finite temperature, we are in a disordered phase. Because if we...
It's not a magnetic field, right?
What?
Is it a magnetic field?
I mean, it could be in a spin model, but...
No, because I mean, if I send h to infinity, usually I order, but okay.
At high temperature?
No, at zero temperature.
I guess. Oh, but I didn't tell you where any labels are on the axis. So. Okay, the only one I'll tell you is that okay, zero temperature is at the bottom of the plot, and high temperature is at the top. But maybe h is negative on the left-hand side.
It's also a fluid sometimes. I mean.
What?
Well, I mean, the high temperature phase, I mean, of real systems, I mean, it has sort of the gas and the fluid phase transition, I mean, so it's a little bit more complicated.
Well, yeah, okay. I mean, obviously this isn't the only sort of picture that one can draw, but this is sort of the simplest one that you expect. If you start with a conformal field theory, for example, and tune a sort of relevant operator through the fixed point, which here is at the middle. Okay. Okay, so the question is, can the situation switch? Okay, can we have A, be an ordered phase, and B, a disordered phase. Namely, you sort of heat the system up and you actually discover order. Okay? So that might sort of seem surprising, but actually the answer is yes, and it's very well known how to do this, at least at intermediate temperatures, or well known in certain communities at any rate. So let me go through a few different examples of how to do this. Perhaps the most famous one, although this was not to me because I don't come from this part of solid state physics, is the Pomeranchuk effect in liquid helium. This was actually very important in the sort of developments in the 60s and 70s to realize liquid helium-3. But the story is basically that if you have liquid helium-3, very high pressure, the ground state is a Fermi liquid. Okay. If you heat this, if you heat the system to a relatively low but non-zero temperature, then at high pressure you find that helium-3 will become a solid. Okay? And why will it do that? Well, in the Fermi liquid, there are sort of isospin degrees of freedom that are sort of locked in place because it's a Fermi liquid. But if you crystallize and you form a solid, these isospins can start to fluctuate because their sort of wave functions don't really overlap. Okay? So this is a system where it starts as a liquid and you heat it and it becomes a solid. It's sort of unusual, but this was, as I mentioned, quite important experimentally to cool helium-3 to low temperatures, at least in the early days. An even older example, which I'm sure was discovered experimentally before understood theoretically, is the Rochelle salt. This is one of a handful of materials where at very low temperatures you have a sort of larger crystalline point group. You heat it, in this case, to about 250 Kelvin, and you find that the point group actually becomes smaller. Okay? So upon heating the system, it loses symmetry, it becomes more ordered. This is another example. A sort of theoretical example that is, as far as I understand, is not so easy to realize experimentally are sort of spin models that have a phenomenon called order by disorder. Anyway, the sort of simplest manifestation of this effect, I would say, is sort of imagining planting a sort of special, a disordered ground state in a phase that would otherwise have been ordered. And so sort of the vast majority of the low energy states, which you sort of sample at finite temperature, are ordered, but you can kind of plant something disordered, or a small number of disordered states very, very low in the spectrum. Okay. And in all of these examples, this is sort of manifestly a transient effect. Okay. So liquid helium, eventually becomes a gas if you heat it to high enough temperature. The Rochelle salt will also be a gas if you heat it to high enough temperature. And in any sort of spin model, as I'll show in a few minutes, there are sort of simple theorems that guarantee that you never order at high temperature, at high enough temperature at least. Okay. So far the story is that, if we go back to our picture, we may sort of zoom in, on some special region in the phase diagram and see that A is ordered and B is disordered. But if we're thinking about, some kind of simple conformal field theory, for example, where, there's sort of no upper limit on the temperature axis, the A phase would continue forever. So far, it sort of seems like A would then always be disordered.
So by disordered, you mean something defined in terms of static correlation functions of local order parameter? Like some
yes, I'll sort of mathematically explain sort of what I want in a few minutes. Okay. Now let's try to sort of make this intuition precise, that indeed we expect that a very large family of systems, or can prove that a very large family of systems are in featureless kind of trivial phases at high temperature. So for much of the talk, I'll just tell you about classical statistical mechanics. The story sort of generalizes with a couple bells and whistles to quantum systems. So in classical statistical mechanics, we're interested in sort of studying the Gibbs ensemble, where the probability of seeing microstate omega is proportional to e to the minus beta h. And I want to imagine that this microstate is taken from a configuration space, here capital omega. This is a set which I will make two assumptions about. The first one is that omega is a sort of product space. So if, for example, you have an Ising model, you have a spin which is either +1 or -1 on every site in the lattice. Okay? And there's sort of no restrictions that like two neighboring spins have to be the same or have to be opposite. You can take any configuration you want. Okay?
Does this exclude gauge theories?
Perhaps, yes. Yeah, we haven't thought sort of too much about gauge theories, but I mean, yeah, I think formally it does. I don't know whether these results could be salvaged for that problem, but I think it would take a little bit more work. Okay. The second assumption, which might seem a little more technical, is that there's a sort of uniform measure, and for the most part in this talk, that means that the set omega is finite. Okay, so we have some k possible spin states in each omega could be different for different sites. And if we have these assumptions, then there's a theorem that goes back to the 70s, which says that if H is a sort of extensive Hamiltonian, it has few body interactions, and sort of one spin isn't coupled to all the other spins, so it's a nice extensive system. Any spin flip can only change the energy by a sort of constant amount. Then there's a sort of beta C, which is not 0. It's sort of strictly larger than 0, such that for any inverse temperature beta smaller than beta C, the Gibbs ensemble sort of describes a disordered phase. One way you can think about this statement is that connected correlation functions will exponentially decay. Okay? This can be perhaps misleading depending on your community. You may think that in the ferromagnetic phase, for example, this would also be true, except exactly at the critical point. When I'm defining this here, though, that would not be true. By these definitions in the ferromagnet, like a single spin correlator would exactly vanish because you're averaging equally over the plus sort of set and the minus sort of set. So this is sort of one way you can think about the absence of order, that correlation functions always are short range. Another way you can think about this is to sort of think about this distribution piece of beta, sort of where is the weight in the configuration space. And at high temperature, the weight is sort of in a giant cluster, whereas in the ferromagnet, for example, at low temperature, you would get two kind of disjoint clusters where almost all of the weight in the distribution is. Okay? And you can think sort of from both of those perspectives, you can prove that there's no order at high temperature. And this can also be done in quantum models. And in fact, it's recently been shown that a much stronger statement holds, for beta smaller than some non-zero beta C, the Gibbs density matrix is in fact separable. So there's a sense in which there's absolutely no entanglement at high temperature in quantum lattice models. Okay. All right.
Separability is weaker than this in some sense, right? Because it allows for classical correlations.
No, but there are no classical correlations either, because the same sort of, the same argument that I'll go through for how to prove the classical theorem also works in the quantum case. Okay. So basically everything is completely featureless. The sort of quantum statement is stronger in that you can't even have short range entanglement. The high temperature Gibbs state is truly unentanglement.
I think, to push in, maybe later work on improve mixing in a very strong sense, right? So, it's more than just looking at correlation functions.
Yes, one can also prove things about mixing. As I said at the beginning, this talk is sort of about equilibrium physics, so I won't talk too much about dynamics, but
No.
this is also
equilibrium statistical mechanics mixing, that's spatial mixing. And, this is just a correlation function, but, what typically is proved is that when you look at, basically any observable, and you prove mixing properties, which, is a very strong form of disorder.
Yes, yes, that's also true. We won't sort of need that for this talk, but that's a true statement. Yes, okay. So let me sort of explain why you can't have long-range correlations at high temperature. There's a sort of very elegant argument that one can make precise. So the crucial thing is that of our assumptions, one of them was that each of these omegas could sort of be enumerated, and there's a uniform measure on the configuration space. And that's important because it means that the infinite temperature Gibbs measure exists. It's just the uniform distribution. And the uniform distribution certainly has no notion of order. This must be in a disordered phase, I think, by any reasonable definition of disorder and order. Okay, and now if we think about sort of turning on a small beta, okay, then we can imagine essentially doing a cluster expansion. This works in quantum systems as well as classical systems. And in the cluster expansion, you find that, this correlator at small beta only vanishes if you kind of pull down a big enough cluster to link sites X and Y. And the size of that cluster, of course, grows at least with the distance between X and Y. This is where these assumptions that H was sort of extensive and each spin could only flip energy by an order 1 amount matters. Okay? It means that sort of each factor of beta H is small. Okay? All right, so that's sort of the mathematical state of things. And certainly 6 months ago, I thought there was sort of nothing to this story because it was already answered. Okay? Let me just sort of make a brief comment. This slide can mostly be ignored, but sometimes people ask me this question about, can't we use kind of dualities in classical statistical mechanics to sort of get some notion of order at high temperatures? For example, if you take the two-dimensional Ising model, there's a famous Kramers-Wannier duality that maps the sort of low temperature phase to the high temperature phase. So surely that gives us some notion of order at high temperature. And I would argue that that's not correct. And the reason is basically that if you sort of track through this duality map, the sort of correlation functions that detect order at low temperature, let's say a 2-point spin correlation function, it maps to something illegal at high temperature, which is a ratio of partition functions. And this is illegal because by my rules of classical statistical mechanics, observables are sort of functions on configuration space that I take averages of. Okay? And in quantum mechanics, this is analogous to observables are Hermitian operators, and I'm interested in expectation values in the Gibbs state. Okay? And neither of these prospects are sort of consistent with looking at ratios of partition functions. So this is a sort of quick argument that we can't sort of just play kind of cute classical games with dualities to try and build order at high temperature. We really have to sort of tackle these theorems head on, okay? Or at least we will. Historically, that was not what was done, though. So there's a sort of long history in quantum field theory of people trying to build systems that order at very high temperature. In many of the constructions, there was some sort of sickness, like the theory didn't live in an integer number of dimensions, so it's a bit funny, or the theory is sort of not UV complete, and so we don't really know what happens at high temperature. But recently, Zohar and Fedor sort of presented the first UV complete conformal field theory that orders at finite temperature. Because the theory is conformal, this means that at all non-zero temperatures, there's spontaneous symmetry breaking in this model. And I'll explain sort of the physics of this model a bit later in the talk after we kind of learn some simpler models. But to sort of introduce it at a high level now, this model describes a sort of n-component vector, phi, interacting with a scalar, a real scalar psi. This theory has a Z2 symmetry, psi to minus psi, which will be spontaneously broken at finite temperature. Okay? And they did a sort of very technical calculation to sort of, essentially find the flow of this theory to a conformal fixed point, to sort of evaluate the saddle point equations at large n, and to just check by brute force that psi picks up a vev. Okay. But at least to us, this was sort of very mysterious, and we didn't really understand at the beginning how this was possible. Okay.
How do you regularize the theory at infinite temperature?
It's a conformal field theory, so it's a sort of well-defined mathematical object in terms of an OPE, etc. One can just do path integrals in the large n limit to calculate the sort of vacuum, so to speak, at finite temperature.
The infinite temperature. I mean,
Infinite temperature doesn't exist.
yeah, exactly. So,
But that's why my wording was very precise. I said arbitrarily high temperature. Okay. So at any non-zero temperature does not include infinity because infinite temperature doesn't exist. This model orders. Okay. And that's still right in contradiction with these theorems that I mentioned, because the theorems didn't just say beta equals 0 is disordered. They said that you can go down to some large but not infinite TC and still you cannot order.
Well, the theorems are not for CFTs, they were for...
That's right.
other context, yeah.
Yes, that's right. So there's sort of no formal contradiction. Let's remember that to sort of prove our theorem, we needed two assumptions. Both of these are sort of dubious in quantum field theories. I think the more interesting one in my view, which is sort of going wrong, is the second one highlighted. This is a quantum field theory with bosonic degrees of freedom. Okay. Even if we try to regularize this on the lattice, there's no reason why necessarily we will have a sort of finite set on each lattice site. Okay. Another way to say this is that the uniform state is not a valid density matrix in quantum field theory. Okay. The identity matrix doesn't have a well-defined trace. Okay. And so the question that I would now like to ask is sort of, what is the physics that underlies high temperature order in this quantum field theory? Okay. How is this possible? Is this just some mathematical quirk, or is there some actual physics that we can unpack behind this construction? Okay. And I will say that, I think we understand the answer to this question if we can take the next step, which is to build lots of new models that also order at high temperature. So we don't just have like one quirky example, but we have a whole zoo of models that are actually ordered at arbitrarily high T. And so for the rest of the talk, I will sort of address these two questions. All right. Any audience questions before I continue?
Yeah, I had a question. You had this statement about entropy in the very beginning that I partially missed, but you were saying the high temperature state always has more entropy. How do you understand that in the context of that of the QFT example you gave?
So that's a good question. So I will punt on that because I'll address that sort of at the end of the talk. But indeed, with hindsight, we will sort of take that perspective quite seriously. So just to sort of remind everyone, remember that just from the laws of thermodynamics, we know that the preferred phase always has higher entropy. So that means that if we have an ordered phase at high temperature, the order must actually somehow be higher entropy than the disordered phase. And this is a point that we'll be emphasizing in the rest of the talk. How is that possible?
Yes. Perhaps you said I missed it. So will you focus on breaking of discrete symmetries, continuous, or it doesn't matter?
We can do both. I'll mostly focus on discrete symmetries, but I could tell you solvable models that they're sort of cartoonish, but there are solvable models that have continuous symmetry breaking in 3+1 dimensions at any temperature.
So this may be related to what Lucas said. So in Young-Mills theory, of course, the expectation value of Polyakov loop is non-zero at temperature. So maybe there's something here that does not account for.
So I think gauge theories are a bit subtle. I guess the gauge theories may sort of have issues with the first assumption. there's another thing which, well, so Luca and I were talking about some things with higher form symmetries last night. I think I have an understanding of why those kind of don't count, but not sort of fully fleshed out. But yeah, I would say that I think to sort of punt on that point, Yang-Mills theory is sort of not in this class. And for the rest of the talk, I'm going to sort of really have in mind theories that obey the first assumption but violate the second one. That's how we're going to avoid our theorem. Okay. But if you try to avoid the first bullet point, there's kind of stupid examples. For example, I could restrict the configuration space to all states below a certain energy in the 2D Ising model. And then even a uniform distribution will look ordered, but it's sort of for a dumb reason. Okay. So I think more interesting is sort of violating the second condition.
Can you explain why a gauge theory violates the first assumption? I didn't understand that.
Well, I mean, maybe it depends on sort of exactly how you want to put the gauge theory on a lattice, but I don't think you necessarily allow for all. Like, oftentimes, if you want to sort of restrict to sectors that obey the Gauss law, that's a sort of not on-site constraint. So the allowable configurations in the Hilbert space will not look like this set omega. Okay. So with this, let me, this quantum field theory is a bit complicated looking, and quantum field theory is hard. So let's play with something simpler. This is what I will kind of lovingly call the classical bosonic lattice gas. The boson here refers to the fact that these n's can take any sort of non-negative integer value, 0, 1, 2, etc. This is a classical Hamiltonian, nothing quantum here, okay? And so I came up with this model. I think it was either Christmas or New Year's. I don't remember which one, but I wasn't enjoying my holiday very much. And so we sort of came up with this model, and then Yichu sort of did a lot of numerical simulations of this model, doing sort of Markov chains to sample the thermal distribution, and what she finds is this. Okay, at low temperature, you see sort of featureless, disordered system. There's little clusters of particles, but there's nothing interesting. And then at high temperature, you see the formation of a checkerboard, okay, where lots of particles are sort of occupying every other site, more or less, of the checkerboard. So this phase spontaneously breaks Z2 translation symmetry, right, because we go from having sort of, in the statistical ensemble, translation symmetry by every site to sort of 2 clusters, one for each checkerboard. So here's a model that I claim order, here's an explicit model. It's discrete, it's on the lattice, and it orders at arbitrarily high temperature. Yes?
So just to confirm, so you didn't put any constraint on the particle number. It's chemical potential 0 and
Yeah, the chemical potential, if you like, is -1. It costs sort of 1 unit of energy to add each particle, but indeed, we're sort of allowing the particle number to fluctuate.
So as the temperature is going higher, more particle, and
yes.
somehow they repel each other, then form some pattern.
Yeah, so indeed, the sort of, and I'll describe the intuition in on the next slide in more detail, but yeah, well, okay, let's just do that. So here's the Hamiltonian again. Remember, so each particle costs 1 energy to put on the lattice, and then if we have 2 occupied sites that are next to each other, we get this energy which is like nu squared nv squared, where u and v are the sites that are adjacent. Okay? And let's sort of I think this is like the simplest argument to understand how this orders at high temperature. So we're going to, at high temperature, think about sort of 2 different potential phases that contribute to the partition function. One of them is the checkerboard phase. So the solid, where every other site on the lattice is occupied, but sort of all the ones on the other sublattice are empty. And because one of the sublattices is empty, this U term just drops out. And then we can just exactly evaluate the partition function. It's a bunch of decoupled sort of harmonic oscillators, if you will. And the partition function scales roughly as temperature to the power L squared over 2, okay, where L squared is, of course, the number of sites on the lattice. And now, the other sort of phase that we might worry about is the one which we saw numerically at lower temperature, which is a sort of gas, where all the sites have roughly the same occupation number. Let me call that n bar 2. But if I have n bar 2 particles on every lattice site, I can't do the computation exactly, but I could sort of intuit that, well, because of this u term, I sort of need beta u n bar 2 to the 4th should be of order 1. Okay? And that tells me that n bar 2, the sort of typical occupancy number in the gas phase, is t to the 1/4. And now I can again sort of estimate the partition function by just counting up the number of these kind of locally low energy configurations, and it's t to the L squared over 4. And I see that t to the L squared over 2 is larger, so the checkerboard phase actually has much higher entropy. Yes?
Is U positive or negative?
If U is negative, this model is not well defined. Because the ends are unbounded, we have to make sure that the Hamiltonian is sort of bounded from below. So U has to be positive. Yeah.
Sorry, why again in the checkerboard n1 is order t?
Because only the first term is there. And so if you think about it, it's roughly like you have a quantum oscillator at very high temperature, and the first sort of order t energy levels are kind of all highly excited.
Shouldn't I find that the second phase wins at low enough temperature? But here it seems like...
Yes, the gas does win at low temperature.
Yeah, but
We can prove that, right? The ground state of this model is unique. It has n equals 0 everywhere.
yeah, no, I'm just saying that it doesn't seem consistent with the estimates because...
But the estimate is at high temperature.
okay, fine.
Yes. Okay. Okay, so we compare our two estimates and we see that the ordered phase wins. Okay. So at high temperature, this system forms a solid. And this solid is driven by sort of the entropy of a very large number of configurations of bosons fluctuating on every other site. Okay. All right. Another reason why we sort of hooked up this model, a little more technical, is that if you sort of think about the limit where u is large in this Hamiltonian, so we can kind of pretend that repulsive term isn't there, at the price of not allowing two adjacent sites to be occupied, this maps onto a very well-studied model called the hardcore lattice gas. In the usual hardcore lattice gas, you think of kind of either putting 0 particles or 1 particle on every lattice site with the constraint that two adjacent sites cannot both be occupied. Okay. And here, normally you think about this hardcore lattice gas by talking about the fugacity z, which is like e to the beta mu, the cost of putting 1 particle into the lattice. And really the only difference here is that the fugacity is given by a different formula. It's 1 over e to the beta minus 1, which is the contribution to the partition function from having 1, 2, 3, etc. particles on each site. Okay? But if u was infinity, this would be a hardcore lattice gas. Technically, this would violate our assumption that the configuration space is a product, but okay, putting that aside, once we have this mapping, we know for sure that this model orders at high temperature because it's well established that this hardcore lattice gas for z above about 3.7 on the 2D square lattice forms a solid. Okay. And not only that, but we also know that the transition between the solid and the gas lies in the two-dimensional Ising universality class. So we might expect that that's also the case of this classical bosonic lattice gas. And we indeed confirmed that with a sort of scaling analysis numerically. So this bosonic lattice gas is it's a gas at low temperature, it's a solid at high temperature, and Ising criticality describes the transition. The sort of new thing is that the solid phase is on the high temperature side. Okay. So I think that this model is, I hope, sort of simple enough that we can really understand what's going on at an intuitive level. And we thought that, it was maybe time to try and rebrand this. So we're going to say that this classical bosonic lattice gas realizes entropic order. Okay? And this jargon means the following. It's entropically ordered because order is one of the degrees of freedom, in this case sort of forming a crystal, okay, kind of greatly enhances fluctuations in another degree of freedom, the boson number. Okay? And remember that we're trying to maximize entropy at high temperature. And so here the point is that we sort of gain more entropy by ordering from the boson degree of freedom than we lose from the order itself. Okay? Thus the name entropic order. It's driven by entropy, not by sort of usual energetic considerations.
I mean, do you accept that this is basically the idea that people talked about with order by disorder? I mean, I totally accept that the example you're talking about is striking because with the unbounded Hilbert space, you have something that persists to infinite temperature, but the idea that you can drive order with entropy is...
Yes, and order by disorder is not the first manifestation of this. The Pomeranchuk effect, of course, predates that by, what, 30 years? So it's an old story, and it's been rediscovered many times. As I said, so John is right. We are not the first ones to think about this. I did want to sort of rebrand this and give it a new name to emphasize, because I think order by disorder is usually referring to a sort of specific family of models, which, as far as I can tell, does not include things like Pomeranchuk effect and Richel solve. But
well, lattice models, not so different from the one you're talking about. But I mean, I think the choice of the term order by disorder was kind of unfortunate because for most people it's not very transparent. But the term entropic order is much clearer. But,
well, I think we agreed with that. We thought it was sort of nice to rebrand this and to emphasize there's a sort of unity between all of these stories that we're telling. And indeed, entropic order is very well established in experiments. It's been found many times. And the contribution that we're making is to sort of explain how to engineer entropic order at very high temperature. And as I'll explain later, we'll sort of build whole zoos of entropic ordered phases, many of which I think are sort of non-trivial, including high temperature superconductivity and superfluidity and topological order.
Sorry.
Yes.
One very silly question. So your classical Hamiltonian,
Yes.
It really doesn't fall into the class of the theorem, right? The classical theorem.
That's correct.
So which part? Which part is different? So
The configuration space doesn't admit a uniform measure. So infinite temperature does not exist. That's why we can sort of beat the theorem. There's sort of no point to do a cluster expansion around at high temperature.
I see.
Yeah, the related question is that is because each site can admit up to infinite number of bosons.
That's right.
So I suppose if you introduce some upper bound.
I'll talk about this point. Yes. Okay. Yes. So yeah, actually, okay. I guess I already made this point in response to the previous question. So an infinite configuration space that's not uniformly measurable is necessary to have entropic order. You could, for example, consider an XY model, which of course has a circle-valued degree of freedom on every lattice site. That also sort of requires the addition of some bosonic degree of freedom to entropically order, and we know how to do that. But yes. Two other sort of kind of high-level remarks about entropic order. So the first is that in some sense this is a finely tuned phenomenon because entropic order is very sensitive to irrelevant couplings. So rather than sort of caring about relevant couplings, which are convenient because usually there's only finitely many of them to think about, entropic order is sensitive to the irrelevant ones. For example, in our bosonic lattice gas, we could add some on-site term like n to the 6. This will immediately destroy the high temperature order for any non-zero value of G. Okay. Now you could ask what happens if we sort of cap the number of fluctuations. The conditions of our theorem now apply, and so we will never order at sort of arbitrarily high temperature. But of course, the temperature at which the order is lost will scale with the sort of size of the cutoff. So I think in this bosonic lattice gas, you would get up to a temperature of order k squared before you see disorder again if you cap the number of bosons at k. So all of the models that I'll describe, there's a few gimmicks that I'll introduce for how to engineer systems with an entropic ordered phase. And even if you can't sort of really realize the pure bosonic model, you could still realize the physics in some regime of temperatures, even if you have sort of only a finite configuration space. Okay. All right. Yes. So the second point that I wanted to make in this talk, right, is if we really understand this physics very well, we'll be able to engineer anything we want with entropic order, any kind of phase we want. So let me show you sort of a few different examples of this. The first will be another magnet with entropic order, but the trick here is useful. So I'm going to take the two-dimensional Ising model, okay, and on every link I'm going to add a boson. So we can have 0, 1, 2, etc. Bosons on each link, and the Hamiltonian looks like this. So A is a positive number larger than B, which we'll also take to be positive. Again, this is sort of necessary to ensure H is bounded from below. We can evaluate the partition function for this model by just summing over the bosons, and we find just the usual partition function for a 2D Ising model. But now at an effective temperature B, which is not 0 as beta goes to 0, but rather approaches this ratio. And if this ratio is sufficiently large, then at arbitrarily high temperature, this system will be in the ordered ferromagnet. So spin-spin correlation functions exactly map to those of an Ising model at this specific temperature, capital B, which can be below the critical temperature. Okay.
What is B?
Capital B is given here. It's sort of the effective inverse temperature of our Ising model. So this is just like a trick to get solvable models that entropically order by essentially transmuting from very high temperature to low temperature by integrating out a boson.
This is not similar to the Kramers-Wanier type trick?
No. Because in Kramers-Wanier, like in this model, we can evaluate honest correlation functions, and they will order at arbitrarily high temperature. Whereas in Kramers-Wanier, remember, you had to look at this unphysical correlation function, a ratio of partition functions, to detect order at high temperature. So this model sort of obeys all of my rules. Okay. All right. So again, we can sort of understand why this is an entropically ordered phase. So in the ferromagnet, again, this is kind of a cartoon. We're not going to get the order 1 constants right, but in the ferromagnet, all the spins are roughly aligned, and each boson costs energy A minus B. And so for each site, we have roughly log T over A minus B bosons fluctuating around. Okay? And if we have the paramagnet, if we have disorder, we get sort of less bosonic excitations because they all cost more energy, A plus B. Okay? But we do gain entropy from the spin fluctuations here depicted as log 2. Because we have a finite number of spin degrees of freedom, this is, of course, a finite number. And so we can see that just subtracting these two numbers, if A plus B over A minus B is a big enough number, we expect that we get more entropy in the ferromagnet by our entropic order mechanism, and that's indeed sort of consistent, of course, with the simple exact solution. Okay. All right. Once you know this trick, you can build all kinds of entropic ordered phases. Many of them feel a bit gimmicky, but nevertheless, they serve as very clear counterexamples to sort of theorems and expectations in the literature. For example, we can take a quantum Hamiltonian now on qubits that's a sum of commuting Pauli strings. This is often called a CSS code in the literature, or you could think of like a surface code or a toric code. And because we have a Hamiltonian, which is a sum of commuting terms, we can play the exact same trick. For each term in the Hamiltonian, we add one of these bosons. Okay? And at high temperature, we can sort of calculate the reduced Gibbs state for the qubits, and it maps exactly to a Gibbs state of the original Hamiltonian H naught at a lower at an effectively low temperature, it's actually the exact same capital B from the previous slide, okay? And if we take this Hamiltonian H naught to be the 4-dimensional toric code, then we find a model that has quantum topological order at any temperature, okay? So topological order, maybe the sort of very crude way to think about this, is it means that sort of almost all states in the thermal ensemble are extremely entangled, and that entanglement cannot be detected sort of with local correlation functions. Yes?
I guess that implies that the U-entang separability result fails for unbounded Hilbert space.
Yes. So this is so sort of to re-emphasize this point, there was a theorem from last year, a paper I cited earlier in the talk that said everything is featureless at high temperature in quantum mechanics and there's no entanglement in the Gibbs ensemble. And this is sort of the most drastic possible violation of that you could find, because actually the high temperature Gibbs ensemble is topologically ordered, meaning everything is extremely entangled. And this sort of simple solvable example tells us that a sort of necessary and a sort of minimal thing that you need to do to violate that theorem is just to add bosons to the problem. Okay.
There was a recent 3D topological order example.
At low temperature.
Yeah.
But it's also, yeah, so you could use that example as well.
Make it.
Yeah, that example, yeah.
It would also work to make the...
Yeah, I think I think it's still a sort of commuting Hamiltonian so that this trick would work. For non-commuting Hamiltonians, we don't know how to sort of do this rigorously.
It's a commuting Hamiltonian.
Yeah, so it will work.
Yeah. I think what do you mean that is topological order? Because you are basically looking at the reduced density matrix, right?
Yeah, so one way you can think about it is that because this Hamiltonian is solvable, you can sort of think about just the eigenstates, like the density matrix is diagonal in a convenient basis. And so topological order kind of means that almost all of the eigenstate, with probability 1 in the thermodynamic limit, you will draw from this ensemble an eigenstate which is sort of decodable in, let's say, the sense of a quantum code. So if I handed you an eigenstate for this 4D toric code, you would be able to correct the logical errors almost surely. This would not be true for the 2-dimensional surface code where you would...
It's not a pure state.
Yes, but what we mean by topological order in the mixed state is what I said.
Yeah, okay.
Another way you can think about it is that you can't prepare this Gibbs state with a sort of finite depth circuit from a product state. Yeah. Okay. For the last part of my talk, I want to sort of go back and sort of give the effective field theorist perspective on entropic order. So now that we have a sort of simple understanding of this phenomenon in these lattice models, let's understand sort of from a field theorist perspective what's going on, and let's explain this kind of weird field theory that I introduced earlier in the talk. So the partition function is evaluated by Euclidean path integral, and we'll assume in this discussion that one of the fields in this path integral is an order parameter which takes on a non-zero vev, so to speak, in an ordered phase. Okay. I don't necessarily like that terminology because we're not in the vacuum, we're at finite temperature, but okay, anyway. There's a sort of standard way that one often tries to do this in quantum field theory, which is to evaluate a one-loop effective potential. Here, this is a kind of one-loop thermal free energy. And the way we'll do that is we will take our fields phi of x, and we'll sort of separate them into the 0 modes and the finite wave number modes, and do a sort of Gaussian path integral over the finite wave number modes. And as long as the sort of vacuum, so to speak, is translation invariant, we might hope that this is a sort of reasonable approximation. Maybe in a certain large N model, it will be exact. Okay. But anyway, once we do this, we get a sort of ordinary integral over all the vacua of phi bar, and we just need to figure out sort of which one of them has the lowest free energy density. That will dominate the thermal ensemble. Okay? And the question is it phi bar equals 0? If the minimum happens to be at phi bar not equals to 0, then we have order. Now, as I mentioned in the beginning of the talk, there's a sort of old history of doing this in field theory. As far as I know, this sort of is attributed to Weinberg, hopefully correctly. And Weinberg introduced what is called a biconical ON cross ON model in 3+1 dimensions. So I have a field little phi and a field capital phi. Both of them are n-component vectors. And I sort of imagine tuning their masses to criticality, so I just have these quartic interactions chosen so that Lagrangian is sort of stable. Okay. And a short calculation shows you that this sort of one-loop effective free energy looks like this. So effectively, thermal fluctuations induce a mass for each of our fields. But because we have two of the fields, we need to sort of think about the sign of this mass. Is it positive or negative? And if you think about a sort of limit where nu is very small, mu is kind of like square root of nu and negative, then this purple coefficient could be negative while the original Lagrangian is stable. Okay? And as soon as we calculate that that coefficient is negative, it sort of doesn't matter what the higher order terms in this Taylor series are. We know that the vacuum is not at capital phi bar equals 0. So we would know that we have symmetry breaking in this model. The purple ON goes to ON minus 1. Now this was sort of done in the 1970s by Weinberg. I believe that he was trying to sort of build a field theory to explain this Rochelle salt phenomena, in his language. But one unfortunate thing is that in 3+1 dimensions, this model is not UV complete. Okay. And so from a field theorist perspective, this is a big problem. It means that potentially the only way to regulate this theory on the lattice would be in some way that restores the symmetry at high temperature. Okay. So the second paper with Chai et al., they sort of wanted to ask, could we find a UV complete field theory that still has this order at high temperature? And they were able to do that, but in 3 minus epsilon dimensions, which is a bit funny. Okay. So, we can go back to this field theory from before in 2+1 dimensions, but now, in this paper, they kind of looked at the saddle point equations. We can now maybe try to look for entropic order by calculating the free energy landscape of this model. So here's the model again. In the second line, I've done a Hubbard-Stratanovich transformation. This is sort of more natural from a field theorist's point of view because sigma, phi squared, these are the relevant operators in this field theory. And you tune to a multi-critical point, which has this sort of Lagrangian in the second line, and an explicit calculation of this free energy density shows you that indeed in this model, psi has a sort of negative thermal mass. Okay. So it's sort of tedious, but one can check this and deduce that this model sort of has entropic order. You can even actually, in this model, calculate just the entropy density and the energy density, rather than the free energy density, and you can indeed see that the entropy is just larger away from psi bar equals 0. Okay.
So here phi is n component vector?
Yeah, sorry, I just didn't put vector indices. Yeah, so psi is a scalar, phi is an n component vector. Okay. Just to say a little bit more about this, this calculation is tractable because we have this sort of large n in the ON model, so you can really integrate out these fields phi essentially exactly in the large n limit. And you can also take into account one loop fluctuations just to resolve the vacuum properly. And what you find in this song and dance is that from this first term, sigma, this is the sort of relevant operator in our field theory, picks up a sort of expectation value, which is of order temperature squared. And the sort of dominant psi squared term here comes with that minus sign. So this is sort of why we're getting a negative mass. Okay. And if we go back to the sort of original pre-Hubbard-Stratanovich Lagrangian, we can sort of think that what's happening here is that we have this large n vector phi, and at high temperature, this vector kind of has a large magnitude. Phi squared is of order temperature. And that large magnitude is kind of pushing psi away from the origin. Okay, it wants psi to sort of lie at order square root nt. And although psi might give itself a thermal mass, this is sort of not enough to overcome the deeper and deeper well that the fluctuations in phi are sort of pushing this field into. And this is the entropic order mechanism at play. If we order psi, we sort of lower the energy cost of the phi fluctuations, which dominate the partition function. Okay. So this mechanism is sort of, in some sense, the exact same one that we've seen before. All right. And again, just to sort of show off, we can try to build new field theories that have new entropic ordered phases. Here's a BCS superconductor. So the first line in blue is a very standard Lagrangian describing sort of fermions, kind of Hubbard-Swiatovich out an attractive interaction, and you get this Lagrangian in blue. This describes the BCS superconductor. And we can couple the order parameter delta to one of these sort of large N bosons. And the saddle point of the one loop effective potential gives us a sort of modified BCS gap equation. And in this gap equation, we see that the coupling is sort of shifted by T times sigma, where sigma is, you know, the same field from before. It obeys a different saddle point equation, but it's sort of morally doing the same thing. As we increase the temperature, sigma acquires an expectation value, which is positive. And it turns out if you analyze this model, the left-hand side sort of wants to shrink in temperature faster than the right-hand side does. And so this sort of maintains the gap all the way until the sort of UV cutoff of our effective field theory.
5 minutes?
Yes. Okay. And so this is sort of at least an in-principle demonstration of how to sort of engineer a high-temperature superconductor. Okay. All right. So the summary is that, you know, entropic order is a sort of unifying mechanism that stabilizes a sort of ordered phase at arbitrarily high temperature. Again, I'll sort of stress that entropic order is realized in nature, and it's been known for a long time. We're sort of rebranding it to try and emphasize there's a sort of unifying and a simple mechanism that one can engineer to do this. And sort of our gimmick is to really build an ordered phase for you at arbitrarily high temperature, and the gimmick is based on the fact that infinite temperature doesn't exist. Okay? So in statistical mechanics, when you have these sort of Hilbert spaces, configuration spaces that don't have a uniform measure, you have to be very careful about how you think about the t equals infinity limit, and it can be the case that you sort of get sucked into an increasingly ordered part of the configuration space at higher and higher temperature. Okay. And I think the last point I'd like to make is that, you know, ordered phases are more useful than disordered ones. If we had a room temperature superconductor, you know, people have been getting grant money for years by saying, you know, we'll have free electricity. You know, a more serious thing is that classical magnets really underlie classical information technology, okay? So we really sort of get a lot of value out of the existence of an ordered magnet at finite temperature. And if we had a sort of quantum topological order at finite temperature, we would have thermally stable quantum computers. Like you could unplug your quantum computer from the power outlet and plug it back in, and your information would still be there. So unfortunately, this latter possibility is quite hard to realize, but of course, if we had such a model, it would be very useful. And so I would like to end with the sort of suggestion that maybe this perspective of entropic order and some of these simple models can perhaps help us to engineer new kinds of ordered phases that are more stable at high temperature to fluctuations. So that's all. Thank you.
So the universal mechanism is always with bosons?
In some sense, you sort of need something like a boson. I mean, it could be a rotor instead, but it has to sort of have an infinite space. Yes.
But in field theory, maybe in field theory, you don't need a boson.
We have not been able to do this with fermions in field theory, and I think part of this boils down to I I don't remember 100%, but I believe when you try to do these things with fermions, you kind of find these, when you calculate this one loop effective potential, the mass is just positive. And it's just sort of this unfortunate thing that I think with gauge fields and fermions, you get positive contributions, and it's only when you have kind of multiple bosons that you can get these minus signs. That may be a sort of way that field theory is telling us about this kind of theorem on the lattice, that bosons were important. I'm not sure though.
Question. Can I ask a question?
Okay.
So, I mean,
I was wondering, just is there a dumber way of seeing that it can't be done with fermions just by looking at that Lagrangian and saying that basically it's important that phi squared is able to get really, really large at large t, whereas if phi was a fermionic degree of freedom, phi squared would, essentially like be bounded, right?
Why would it be bounded?
Well, because if it was psi dagger psi, that's occupation for fermion on psi.
On a lattice.
Yeah. I mean, I sort of share your intuition, but
Hardcore boson.
Yeah, but in the continuum, there's no.
Okay.
yeah, I mean, I would agree with Luca that I think in the continuum, this is a very delicate statement to make. Certainly on the lattice, that would be my expectation, but in practice, it turns out to be very hard to do this with fermions, if not impossible, and I think that may be related to the lattice theorem, but I don't know if there's a deep connection.
Okay, this might be a very stupid question, but like in nature, like if I have an experiment, I have a sample. There's always some bosons around, right? Some like light or whatever. So now when I heat this one up, I don't excite the bosons of the. I mean, I somehow excite the bosons of the radiation. Like I do this because there's black hole radiation. But like, why? Like, what is the interaction that you need like in the bosons in your model to kind of get this effect?
So I would say that, all of these models, the way that the bosons interact is very special. If you throw in sort of generic bosonic interactions, this won't work, and that's sort of the situation I'm sure that you're seeing in most experiments. You kind of have to engineer something special with how bosons interact with themselves or other degrees of freedom to have high temperature order.
Like in your models, the bosons don't interact with themselves at all, right?
No, they do. So in the bosonic lattice gas, setting G equals to 0, the Hamiltonian was like this. It's certainly an interacting system.
Okay, in this case, but in the other cases with like, it's just like.
But, okay, the bosons are sort of fundamentally interacting with spins in this case. So it's not like, if you had a non-interacting boson sector, then, the bosons would just be integrated out and there's nothing left. So they do have to.
Do you have any idea what kind of, how you could like engineer a system that would have this?
In the lab?
Yeah, I don't know.
We would like it if someone comes up with it. It's not really my forte, but.
Yes. So if you think about these high temperature phases, a lot of them look kind of strongly random, even in the way they're ordered, because the bosonic occupations are going to be fluctuating pretty strongly.
Yes.
Is there a notion of like they might be stable to like adding small non-commuting terms because they kind of because there's localization?
That's an interesting question. We haven't thought about this, but we have. I would say we would like to sort of think about like taking this model and adding quantum fluctuations to it. I don't have a sort of. I think it's a challenging problem, but it would be interesting to sort of.
These papers by Uveniers and Durup from like a bunch of years ago, basically looking at like bosons, strongly anharmonic bosons at high temperatures on the lattice. And the idea is that at high temperatures, the conductivity vanishes in some like faster than power law way because your nearby sites are so far off resonance to each other, you can't move things around.
Mm-hmm.
So it seems like that kind of mechanism would apply in your systems as well.
Probably, but yeah. Well, I'm not sure. It could be more subtle, but maybe, yeah. In this model, somehow it's not necessarily off-resonant because the on-site term is linear.
Yeah, okay, yeah.
So
the other one, for example, has a quadratic.
Yeah, so in a Bose-Hubbard model, indeed, I think that, their story is right, but here you might actually have a sort of very high temperature superfluid. I'm not sure though.
I mean, if you look at zero temperature, you have still zero entropy or not?
In this model, so when I first wrote down this model, I didn't have the +1, and Zohar and I argued about this for months. Because of course, if you don't have the +1, then there's a 2 to the n fold degeneracy in the ground state, and he didn't like that. And I was like, whatever, it's like spin ice. This is a sort of common phenomenon. But I gave in the end, and if you have the +1, this model orders at all temperatures. And yeah, you have a 2-fold degenerate ground state. It's just the standardizing model.
Okay. Thank you again.